Welcome to Electronic Specify Insights, the podcast for electronics engineers. I'm your host, Paige West. The All-Electric Society is a vision of a world powered by clean, affordable and accessible energy, without harming the environment or the economy. To achieve it, we need three connected pillars: digitalization to make systems smarter, electrification to replace fossil fuels with renewable energy, and automation to optimize everything from industry to daily life. By combining renewables with advanced digital technology, we boost efficiency and enable a long-term shift to sustainable energy systems. The future is electric, and it's already beginning. Want to learn more? Check out the Avnet Abacus website for all the details at my.avnet.com/abacus. In today's episode, I speak with Aditya Ambada, Business Unit Manager at Diodes Incorporated, to explore the vital role of digital isolators and isolated gate drivers in high voltage power systems. With applications ranging from industrial drives and solar inverters to electric vehicle chargers and data center infrastructure, these components are foundational to performance, safety and reliability. We'll discuss the key design considerations, regulatory requirements, and how isolation technology is evolving to meet the demands of next generation electrified and intelligent systems. I hope you enjoy this episode. Let's get started. Hello and welcome back to Electronic Specify Insights. Today I'm pleased to be joined by Aditya Ambada, who is the Business Unit Manager at Diodes Incorporated. So thanks very much for joining us. How are you today?
I'm fine. Thank you, Paige, for having me.
You're very welcome. Why don't you start by giving us a brief introduction to yourself and your background?
Absolutely. Hi, I'm Aditya. I am Business Unit Manager for Switching Power for Diodes Incorporated. My business unit is responsible for power products like DC to DC converters, AC to DC converters, USB PD power, and isolation products such as digital isolators and gate drivers.
Fantastic. And for those of our listeners who perhaps aren't familiar with the company, can you also introduce Diodes Incorporated for us?
Diodes Incorporated is a leading global manufacturer of semiconductors with broad portfolio covering discrete devices like our namesake diodes and transistors, as well as analog, logic, timing, and power management ICs. We serve diverse markets from automotive and industrial to consumer electronics and computing. In the context of this discussion, we have been expanding into power products over past few decades or so, and we are investing in high voltage isolation solutions as well. We have leveraged our expertise in power semiconductors to develop new digital isolators and isolated gate driver products that meet strict safety standards and also provide high performance for our customers.
Fantastic. So to kick things off then, can you explain for us what digital isolators and isolated gate drivers actually do and why they're so critical in high voltage applications?
Digital isolators and isolated gate drivers are basically semiconductor devices that transfer signals across an electrical isolation barrier that enables communication and control between high voltage and low voltage circuits without any direct current flow. In essence, they're providing a ground isolation. The two sides of the devices share no conductive path, which protects the low voltage electronics from the high voltages present on the other side. A digital isolator typically transmits data, which is basically logic signals across the insulating gap via capacitive coupling, which is inside the chip. This allows microcontrollers, sensors, or communication interfaces on the low voltage side to send, receive signals from components on the high voltage side or vice versa. This isolation barrier withstands very large voltages, and this difference can be in kilovolts range. So the transient surges or falls on the high voltage side do not harm the low voltage side. For isolated gate drivers is very similar to a digital isolator. It not only transmits logic control signals, but also provides a high current drive needed to turn up power transistors such as IGBT, MOSFET, or silicon carbide or GaN transistors on and off. These are critical in power electronics. For example, in a motor drive or inverter, the gate driver receives PWM control from low side microcontroller and sends corresponding high current pulses to the gate of the high voltage transistor, all while maintaining isolation between the low voltage side and the high voltage side. If we didn't have these isolated gate drivers or digital isolators, it would be nearly impossible to interface a low voltage control system with a high voltage or high voltage high side transistors and half bridge or full bridge inverters. This isolation kind of allows the nodes to float at the high voltage side and drive or have communication go through these two planes. The primary design criteria and the most critical criteria is actually the safety. You want to make sure that the low voltage side stays safer for human interface and things like that. And it ensures that if there is something going on the high side, something wrong going on the high side, such as short or surges, the high voltage cannot reach to the user accessible circuits on the low level electronics. The isolation is often reinforced. Sometimes it's like 5 kilovolts RMS, and the surges can go for 8 kilovolt. And for diodes products, we can even do 10 kilovolts protection, so that we can reliably protect the low side circuits. Another critical aspect is now noise and ground balance management. High voltage systems often involve parts of the circuit at very high voltages and high ground potentials. If you try to connect them directly, you would create ground loops or impose large common mode voltages that can corrupt signals and possibly damage circuits. Digital isolators and isolated gate drivers, they both break this ground loop, allowing a clean communication link and interface between low voltage and high voltage, which are immune to these common mode voltage differences. They typically reject large common mode transients, so even when high voltage switches turn on and off rapidly, causing sudden DT swings, the signal integrity is maintained. And this ability is often called common mode transient immunity, CMTI.
Excellent, thank you. So I'm interested to hear what trends you're seeing that are driving demand for these components in the industry.
It's basically the electrification trends with the modern electronics that are boosting demand for high performance isolation components. There are various industries pushing for high power and greater efficiency. The power rail voltages are getting higher, and so are the needs for isolation products increasing. For example, in electric vehicles and charging stations, in EV, the battery voltages are generally around 400 volts to 800 volts that are used to drive the EV motors. There are also low voltage domains in the EV car, which are 12 volts or 5 volts, like infotainments, where people can touch the screen and so on and so forth. So, to control this, to supply for motor or inverters in EV or for infotainment, multiple isolated gate drivers are being used today to drive silicon carbide or IGBT transistors. Basically, there's a lot of power conversion happening from high voltage domain to the low voltage domain. Similarly, digital isolators are used to transfer critical parameters that are being monitored on these boards across high voltage and low voltage domains in the system. Similarly, in data centers, with the escalating power demands of AI systems, these data centers are adopting higher distribution voltages, like 300 volts, and maybe it can go actually even higher. And they are trying to adopt this from the EV architecture. So this shift enhances efficiency because you have higher voltages, you're actually running lower current, so the conduction loss is lower in this kind of system. As an EV, isolation products are now critical in data centers as well for now, because there's higher voltage in these data centers in the backplane. Similarly, in energy sector, solar inverters are operating at higher voltages, higher string voltages. That's about 1500 volts DC, driving demand for robust isolation in both inverters and DC-DC converters. I believe isolation products like digital isolators are critical to the system, especially for the power grid kind of infrastructure where You want to make sure that the maintenance crew who's doing any kind of work on the monitoring panel on these electric grids, they don't get shocks and so on. And also we see a lot of global electrification trend and IoT trends. They're making systems have a mix of high voltage power and low voltage digital intelligence. Whether it's an electric robot arm in a factory or a smart transformer in the grid or a medical imaging device, all these require isolation or safety and proper operation. Thus, as these industries evolve, the underlying isolation technology is a critical enabler, and the demand for the reliable, high speed isolators will keep rising.
So, when engineers are selecting these digital isolators or isolated gate drivers, what would you say are the key specifications that they should prioritize?
There are several key specifications that they should keep in mind. Firstly is isolation rating. That's the working voltage and withstanding voltage. And this is the fundamental spec that any isolation device should support. And that's the necessary working voltage. Continuous, basically, it's a continuous voltage across the isolation barrier during normal operation. It should actually stand. There are different ratings. Common ratings are 2.5 kilovolts RMS, 3.75 kilovolts RMS, 5 kilovolts RMS, or even what we call reinforced isolation with 5.7 kilovolts RMS. For example, if you're designing a 1200 volt system, you would likely want to use a device that is certified for a 5 kilovolts RMS reinforced isolation. You also need to look at the surge voltage rating. That is how it handles the short spikes on this high voltage rail, like 8 kV surge immunity for IC 60065-1 standards. You need to actually comply to that 8 kV surge. Always choose a part that meets or exceed the safety standard requirements for your end equipment. You don't want to push the device you're using at the very edge, have some margin on that. The second one is we talked about CMTI, common mode transient immunity spec on the device. It's absolutely vital in electrically noisy environments like motor drives or automotive, or a harsh industrial environment where there's a building machine or a power converter where large swings of high voltage spikes can happen on the high voltage side. So CMTI's capability of isolator to reject or withstand a rapid change in common mode between the two planes. So it's usually specified in volts per nanosecond, V divided by NS, or the equivalent kilovolts per microsecond. So high value means that voltage or that isolator can handle is very steep. For example, and if the CMTI is insufficient, you would observe issues like spurious resets or miscommunication between on the digital isolator channels. You will have bit flips, like when you're transmitting data on the digital isolator channel, might flip, the bits might flip and causing an error and resetting the communication protocols. Gate drivers are very similar. They usually do very fast, high voltage turn on and off. And they can be affected by the CMTI as well. They might false trigger a FET. You might, turn on the transistors on both high side and low side, creating a critical failure or shoot through in this case, what we call. In real terms, considering an inverter that switches around 600 volts in 50 nanosecond, there's a 12 volts per nanosecond slew. If an isolator CMTI rating is saying 10 volts per nanosecond, that 12 volts per nanosecond event might induce a glitch despite the isolation, because the common mode changes is faster than the device immunity. So you want to pick device, for example, which is for systems like which are 800 volts and they have a 8 nanosecond kind of turn on time. They should have basically more than 100 volts per nanosecond kind of spec on the board. So it's very critical for these kind of application. Then there is data rate and propagation delay that needs to be taken care as well, and that's signified by what is the speed. For example, if you're looking at digital isolator, you need to make sure that you have enough speed on the digital isolator for your communication between the high side controller and the low side controller. And that way you don't have any problems transmitting the data as fast as you can. So typically we'll see around 100 Mbps on digital isolators. That's most likely most of the applications are okay, and in future that might even change higher. Then we also have channel count and direction, because when we're talking about digital communication between the different systems, you'll have some channels going from high side to low side, and then some channels going from low side to high side. So the channel counts is also another critical criteria, and you want to see, like, how many channel counts you have in a package, or how much isolation you want to have between these devices. And for the gate drivers, of course, drive strength is very important. If you're driving high current system, you need to make sure that your driver can handle higher amperage to drive these silicon carbide FETs and so on. So typical values range between 2.5 amperes to 6 ampere. And for example, our device API 2155, which we're working on, those series of gate drivers will offer 4 amperes and 6 ampere drive solution, which are suitable for driving sizable silicon carbide MOSFETs directly. Our gate drivers can pair pretty nicely with our silicon carbide MOSFETs from diodes, DMW SH120 series and 170 series of standard and automotive qualified devices. Then we have other critical aspect we don't talk about much is package and creepage. Like, all of these high voltage systems have creepage requirements that you need to comply with. So high voltage isolation products often come in wide body SOIC packages with 8 millimeter creepage to meet reinforcement standards. So we do give both 8 millimeter creepage clearance, and we also have narrow body packages which are 4 millimeter creepage for space constrained and less critical isolation specification. So we do have that opportunity for designers to choose from. Then we have certification and reliability, and that's one of the key things for all the designers to look at, because most of these high voltage systems would have to go through certification like UL, VDE, CSA, CQC for isolation. This simplifies your product certification if the device that you're using, the isolated device you're using, is already certified. So that you need to take care of. If choose devices which already have the certification done on them, and if it's an automotive device, make sure that you're picking automotive qualified devices. And those are the some of the key things that engineers have to look at, and between these they always have to optimize what is more critical for them versus the other.
Brilliant. No, I know our listeners will appreciate that deep dive. Thank you. I'd like to come back to the CMTI. Considering its importance, how is Diodes Incorporated addressing this?
For silicon or GaN type of switches, they usually have very fast edges, and CMTI becomes a very, very critical spec for that. We at Diodes are basically coming up with digital robust ISO family of isolators that we are designing with very high CMTIs. For instance, our API 772X family guarantees at least 150 volts per nanosecond, and typically even higher in practice. So to put that in perspective, is 150 volts per nanosecond means a 1500 volt spike occurring in 10 nanosecond would be handled without upsetting the signal. That means that's a very, very rugged spec there, which covers most application in real world transient scenario. Competing older generation products, you'll see that they're around 50 to 100 volts per nanosecond spec. So that kind of puts some of these faster moving, moving application where you need to have, faster switching at the marginal spec. So that's one of the things we have done. We have actually put the 150 nano volts spec on those. Our products also use a thicker insulation barrier and differential signal transmission, which inherently gives better common mode rejection. The disturbance tends to appear equally on both differential lines and cancel out. That's how it works. Our isolators have also carefully designed CMOS input and output stages that prevent any parasitic coupling across the barrier, which also improves the noise filtering, and we also have a deglitch logic on the output. Our robust ISO capacitive barrier coupled with differential signaling and glitch filters yield a very good CMTI performance. And in practical terms, our isolators maintain robust signal integrity even when exposed to very fast switching edges and noisy environments.
I'm interested to hear what role does packaging play in the design of isolation systems?
It's actually very key spec in design and performance of isolation products, particularly when we are talking about voltages that they can handle and how much board space they can consume. In fact, when we talk about isolators, we often implicitly talk about their package type. For example, wide SOIC or versus narrow SOIC, because it directly affects what is the creepage distance or clearance and insulation capability. Creepage and clearance are distances mandated by safety standards. Creepage is the path along the package surface between high voltage pins, and clearance is the straight line air distance between those pins. So, to achieve higher isolation rating, especially reinforced isolation, you need a larger creepage. That is why many high voltage isolators come in wide body packages. That's, for example, SOIC 16W, which are about 10.3 millimeter wide. And as opposed to something like a standard packaging, which is 7.5 millimeter wide, SOIC 16N. So depending on the isolation, how higher you want to go, your package also widens. Wide package can provide 8 or more creepage along across the molding compound. That's the black material that the ICs are made of, which is a common requirement for reinforced isolation at mains voltage per IC 60950/62368 spec. We also have isolators with wide SOIC 16 packages to achieve 8.3 millimeter creepage, allowing 5.7 kilovolts isolation rating. If the engineer's design is constrained, they can use a smaller package as well. But it depends on what is the give. If they really want a higher isolation rating, they need to pick a higher or wider package in that case. The other thing we are doing is it pertains more to digital isolators. We are putting multiple channels in the same package. We are coming up, and the first we'll have is 2 channel released. We'll also have 4 and 6 channels coming in a few quarters, which allows and gives users a little bit flexibility in how much transmission lines they are digital signals they can actually pack in one single package. So that kind of helps, integrating more channels into the same package, saving the board space as well.
Brilliant. Now you've mentioned a couple of standards so far throughout. Can you tell us how your products meet global safety standards such as UL, VDE, and IEC? And are there any emerging regulatory requirements that system designers should be aware of?
Absolutely. We ensure our isolators and gate drivers meet or exceed some of these relevant standards, and I'm going to explain some of them briefly on those and talk about some of those. We recently launched some products, and we are undergoing certification as well. One of them is a UL 1577, which is a US safety standard. Specifically, it was meant for optical isolators historically. Now it's being applied to digital isolators as well. It involves a 1 minute dielectric withstand test that is typically 5 kilovolts RMS for reinforced isolation for each production device. That means each device needs to actually comply with that. And our devices are rated up to 5.7 kilovolts RMS, so we easily pass that spec. For VDE, that's the German test agency, their VDE standard is 0884 10 11. These are basically based on IC 60747 17 for digital gold standard for isolator safety. It defines functional, basic, and reinforced isolation classes with specific working voltage and surge voltages that we talked about. And most importantly, they also talk about partial discharge requirement. And partial discharge testing is crucial for longevity. It checks that no tiny discharges occur within the insulation at high voltage, which would degrade it over time. It A device like our isolator might be certified by VDE for reinforced isolation up to, for example, 3 kV working voltage. Just is an example, meaning it's cleared for use in the system up to that continuous voltage. VDE certification is highly regarded internationally. Many European and Asian customers specifically look for it. We design our isolation barrier with materials like thick silicon oxide that inherently have high partial discharge inception voltage to comfortably pass VDE testing. Then we talk about IEC standards, the IEC 60747 5 5 and IEC 60747 17 are standards for optocouplers and capacitive magnetic isolators. They mirror a lot of the VDE standards. The latest one, IEC 60747 17, specifically addresses non-optical isolators and lays out the test methods for them. So it's relatively new and provides clarity on how to classify isolators in terms of isolation. Our isolators are designed in alignment with these standards as well. The other thing that's emerging now is, and that's especially in Europe, is the concept of functional safety. It's not directly related with the isolation, but it's a standard called ISO 26262, IC 61508, applied for components. While isolation components themselves are safety enabling, some ask for proof that a component is reliable to a certain probability under normal operation. This is not a direct isolation standard, like I said, but for example, it's an automotive requirement, and they might require to develop under certified process, which is this ISO 262, to provide a fit rate for random hardware fault calculation. And from diodes, we can actually provide for these applications as well all the requirements for AEC 100 qualification for automotive isolators, and we can share the reliability data for safety analysis for our customers as well.
Brilliant. Thank you very much for that breakdown. And following on from that, how do your isolators maintain signal integrity in high EMI environments? For example, such as inverters or motor drives.
They're kind of torture tests for isolators. We tackle this through combination of differential isolation technology, shielding, internal filtering, and robust circuit design. So we do a lot of design kind of changes on the chip to make sure that we can work properly in high EMI environments. The basic thing is that we need to make sure that when there's a high EMI, your devices don't create, they have a minimum jitter. We have a correct duty cycle going for a isolated gate driver from one side of the controller to the FETs. So we make sure that we comply to all of these, noisy environments, and make sure that we have a reliable out of the box solution. In many cases, our isolators are simply EMC compliant for the whole system because they inherently reduce the chance of noise-induced malfunctions with the input filtering we have already on the circuits.
Excellent. And I'm interested to learn what innovations has Diodes introduced recently in this area, and are there any future developments on the horizon you can tell us about?
Absolutely. We have what we call robust ISO family of products. It is our in-house isolation technology platform used in the new digital isolators, API 772X family, and the gate drivers which are coming in, API 2155X family. The hallmark of robust ISO is significantly thicker insulating barrier. That's the capacitive barrier in there. That has been what has been typically used. We actually use a thicker, greater than 25 micrometer thick silicon oxide polymer dual barrier compared to the usual 10 to 20 micrometers what we see in the other products. This yields exceptionally high breakdown voltages and reliability. For example, our devices have been tested to have higher breakdown margin. In one internal test, we pushed our devices and other similar devices to failure, and diodes isolators withstood a higher voltage before breaking down due to the thicker insulation. We already talked about high CMTI for our devices. Additionally, we have built-in protection features. For example, the API 21550 gate drivers that you'll see coming in has an integrated gate overshoot protection circuit and deglitches on the disable pin. These are some of the innovations to improve the robustness of gate drivers under real condition. For example, preventing a Miller-induced false turn on by clamping gate if it overshoots, and filtering any noise on the enable line that could disable the driver. So we make sure by circuit design we actually take care of that. When I speak of digital isolators, we introduced enhanced fail-safe logic. If an input side supply goes down or if no signal is received, the output goes to a default state after a defined timeout rather than chatter. So that kind of gives a better capability for designers to make sure that they know when there is a failure mode, what they do with that signal. So while, you know, with all these circuits, we also make sure that we have different package options for these, both digital isolators and gate drivers. We introduce a wide body SO16 package with an extra wide creepage. We call it SO-16W. WW. Both the digital isolators and gate driver family of devices will be available in automotive grade as well. And we will have multiple products coming in as we complete this family. We'll have 2 channels now, 4 channels, 6 channels, and the various configurations for the gate drivers as well that will be releasing shortly to market.
And given all that you've told us today, how do you see isolation technology evolving to support these next generations of electrified and intelligent systems?
As system go in future, it's hard to predict the future, but we have seen some leading indicators. We are seeing some 800 volts EV architectures now. They'll probably keep going up, if certainly not down. We have seen some grid connections at higher kilovoltage levels for renewable farms, and we also think that as we go forward, the speed requirements on these isolated devices will actually increase. And we believe that we'll have more and more customers asking for more diagnostic features in some of the functional safety application in automotive. But those are some of the trends we are seeing that might happen here.
Finally, then, what is your one piece of advice you'd like to give our listeners who are perhaps designing high voltage systems who might be underestimating the role of isolation?
I would say plan for creepage and clearance early on when you're doing the design. Match the isolators, like what kind of voltage, what kind of speed you're looking for your use case. Third, I would say test under real conditions. What's expected worst case when it's going to those kind of environments, and stay updated on the isolation tech. There are different devices coming in, newer products coming in, and keep up to date with those.
Fantastic. Is there anything else that you'd like to add before we wrap up?
Yeah, sure. We have robust ISO technology products, and Diodes also has silicon carbide MOSFETs that can help customers to complete high power application. So feel free to reach out and try our products on diodes.com.
Fantastic. I'll certainly encourage our listeners to do that. And thank you very much for joining us today. It's been a pleasure hearing more about the company and innovations that you're working on. And I know our listeners will have greatly appreciated your insights. So thank you very much.
Thank you.
The All Electric Society is a vision of a world powered by clean, affordable, and accessible energy, without harming the environment or the economy. To achieve it, we need 3 connected pillars: digitalization to make systems smarter, electrification to replace fossil fuels with renewable energy, and automation to optimize everything from industry to daily life. By combining renewables with advanced digital technology, we boost efficiency and enable a long-term shift to sustainable energy systems. The future is electric, and it's already beginning. Want to learn more? Check out the Avnet Abacus website for all the details at my.avnet.com/abacus.
Thank you for listening to this latest episode of Electronic Specifier Insights. Don't forget to subscribe to the series to keep up to date with our newest guests, and do share with fellow colleagues, friends and family who may be interested in the latest news from the electronics industry.